Recording. So today is going to be a more traditional lecture. Specifically, hopefully this works. Give me a second. Okay. Yeah, there we go. Okay. Let's go ahead and exit Steam. All right. So today we're going to be talking about for loops in the context of approximations of pi. Now, pi, I know for a lot of you, is just simply a number in a formula. It's got a weird symbol, a Greek symbol, and it's referred to as, and we just call it 3.14159. It's just you typically just plug in 3.14. The question is, how in the world did we get this number in the first place? And the answer is that this number is a ratio. It represents the ratio, as it says, of a circle's circumference to its diameter. In other words, it's the ratio from how big it is around to how big it is going through the middle. Okay? And part of the reason why I love Wikipedia, particularly the math, science pages, those tend to be really good, is that they have a number of really good animations. So here we have a unit circle, right? It's got a diameter of 1, is a diameter of 1, meaning it's 1 across. So if we just roll it out, right, if we take that and roll it out, unrolled, the circle would leave a length of 3.14, about. Well, 3.14 and a bit. Right? That's what the ratio. That's what we mean when we say it's a ratio of the circumference to the diameter. Okay? Everybody following so far? Right? Now, it is what we call an irrational number, meaning that you cannot take you can't take a fraction and set it equal to pi, and get and say this is what pi is. You can use a fraction to approximate it. And that's what was done throughout a lot of history. 22 over 7, as it says here, is a common one. There were number ones, let's see. Of course, since it's Wikipedia, right, 355 over 113, I think, was a one that was discovered at some point in China during, much earlier times. And there's a lot of different ways of calculating pi. Okay, these days with computers, we use extremely powerful algorithms to calculate pi. So this is what we call a log scale, where basically the scale on the y-axis is not measured linearly. So going up by 10, so instead of here 1 to 10 is a difference of 10 of a magnitude of 10. It doesn't go 1, 10, 20, 30, 40. It goes 1, 10, 100, 1,000. It's a very large jump between each of those lines. And what this is charting the number of digits of pi that has been successfully calculated, right? It's an irrational number, so it goes on forever. So the number of digits it has is infinite. Now, going beyond a certain number of significant digits is kind of just flexing at some point. In fact, that's what this is what this is over here. It's flexing and showing off new algorithms or showing off the power of computer processing. But we can see with the advent of computers, we went from being able to successfully calculate about 1,000 digits, slightly under 1,000 digits of pi to 10 to the, I don't even know what 10 to the 14th represents, but it's more than billions, It's quite big. So, yeah. So the question is, you can say, okay, with a computer, we can just plug in an algorithm and it will do that. But how did you actually calculate pi back in the day? How did you come up with an approximation to get more digits? So there's a lot of different, and just like we did on Tuesday, the answer was, well, if we got something close enough, it would be good enough for calculations. So just like how we use 3.14 in a lot of elementary classes, that's perfectly fine. So let's see. Now, particular formula we are going to be looking at today is called the Madhava-Leibniz series, which is this formula. Okay. We basically, and so they get so things in mathematics these days get names like this where there's hyphenated, because it was originally called the Leibniz series or Leibniz formula for pi, because that was originally who we knew discovered it. Except, when you've got multiple cultures around the world, each with mathematicians who are really into math, and they have no way of instantaneously communicating with each other in a common language, there's going to be a bit of repeated work. And that happens over and over and over again, where mathematicians of different cultures each come up with the same formula or the same thing, and it just takes a while for people to figure out, oh, this guy discovered it before this guy. So now it's called the Madhava-Leibniz series because we know that Madhava of Sangamagrama and his I don't even know if I pronounced that right, or his followers in the 14th to 15th century discovered this in India, and then this was independently rediscovered in 1671. So quite the gap between there, hundreds of years. But again, nobody was able to instantaneously communicate with each other in a common language. So the science doesn't spread very quickly. And so what is this formula? It's a way of calculating pi over 4, or pi. Okay? Specifically, let's focus on this. It says that pi over 4 is equal to this infinite series, which is something you learn about in Calc 2 at some point. So, and if you don't, that's fine. Just know that these things can go on either forever or for an arbitrary length of time, right? And the longer that we continue this a particular formula, the closer the answer is actually going to get to this. So this says that 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th plus a 13th minus a 15th plus a 17th, because it's a pattern. If you keep doing that over and over and over and over again, you're going to get closer to pi over 4. It's also, as you can see on this page, formulated as pi is equal to 4 times this, that infinite series. You can do that with infinite series. Okay, both come up to the same thing. So we want to calculate this formula. Okay, so that's what we're going to be working on today, using this formula to calculate pi over 4. Now, the issue is, manually trying to type all this out is a pain, right? And we'd be limited by what we could do by just simply typing 1 minus a third plus a fifth minus a seventh, and then for every digit we wanted to add, we'd have to go through and make sure we typed and didn't make an error when we were typing, it's its own thing. Instead, it's better to just do it automatically. So I brought up a tool that we had on. So I'm going to re-examine a tool that I first brought up on Tuesday, and it's going to be the focus of the assignments of Lab 4 and 5. I know we're still stuck on Lab 3. You can use this on Lab 3, but the entire point of this is because this is like the topic that we will be talking about for the next couple weeks. This is the hurdle to pass coding. This is it. Okay? If you can get this and do well with this, you're probably going to be able to do just fine in this class. If you're struggling with this, you need to make sure you put in the work so you can do fine in this class. Okay? So I'm going to go ahead and make a Python file to do this for Leibniz. Okay, and so what did we learn today? What did we learn last time? We learned how a for loop works. What we said, what I came up with last time is that we have these 3 separate types of statements in programming languages. And I said we have the imperative statement, which is we just do this. We just tell it to do a command, and it does the command. We also have the if statement, or the conditional statement more formally, which just basically gives us kind of a flow chart. If it's one thing, do this. If it's the other thing, do that. That's a tool we'll be looking at later. We haven't introduced it yet. The third tool is the one I'm introducing now, which is the iterative statement. This is the third type of statement, and it's a really good tool for being able to do things repeatedly. Okay? Now, we'll learn, and this is the for loop. So we typically write it in for x in y. This is the format where x and y are fill in the blank, okay? So, and the way I wrote it last time was for blank in range 5, why not 4? And then a colon at the end. The colon is always necessary. The for and the in are always necessary. It's the blank and the range. It's this over here that's going to change, and this over here that will occasionally change. Okay? For blank in range 4. Print hello. So the for loop, when we see it in this format, this range format, it simply says, okay, whatever's in the number for range, I'm going to do whatever's inside this for loop, I am going to do it that many times. So this for loop says it's going to do it 4 times. I'm going to change that number because I'm saying 4 and 4, right? So might as well change that. So that did it 4 times. Let's go ahead and do it 3 times. So this for loop is going to go 3 times. Hello, hello, hello. Whatever's inside of it, it's going to do. Print A, print B. Okay? Hello, A, B. It did everything inside of it, so it's going to do it again now. Hello, A, B. And now it did everything inside of it, so it's going to do it again. Hello, A, B. Okay? Later on, one of the big things we do, throughout the semester, including today, is do something called an accumulator. Total is equal to 0. Right? So let's go ahead and just kind of work ourselves to this endpoint. Print total. And we'll go ahead and remove this A and B just for good measure. This is going to change a lot as I'm doing it, so don't stress out if you're having trouble keeping up with copying down the code. This is why I take a video, right? This is why I do the video. Okay? So run it. And let me actually shrink my face in this video because I'm going to be blocking the output otherwise. Boop, boop, boop. There we go. Okay. So here we have total is equal to 0. We tell that we have a for loop that runs 3 times, and we print out total. Total is equal to 0, right? Nothing changed during this time, so we print out 0 for total, right? Okay. So total is equal to total plus 1. I went over this yesterday. This is a perfect, or I went over this once already, and it's been in the videos. This is a perfectly valid statement in Python. This says, remember, the equal sign, think of it as an arrow. Take what's on the right, put it in the left. So we say total is equal to 0. 0 plus 1, we take that sum and store it in total. We compute it, and we just happen to be storing it in the same place that we used that we had a variable in the formula. In a variable that we had in this formula. So 1 gets stored in here, and then we do a for loop to print hello 3 times, and we print out 1, right? Because no sleight of hand there. And if I moved it down here, right, over here, where I said total is equal to total plus 1, it's still going to be 1 because it's outside the for loop. It's not inside the for loop, right? Inside the for loop means it would have to be indented inside the for loop. Like so. Because you knew that was what was coming, right? So total is equal to 0. For blank in range 3, print hello. Total is equal to total plus 1. So we're going to do this statement 3 times. So the first time, we'll print out hello. Then we're going to say 0 plus 1 is equal to 1. Store that in total. So total's now 1. Now we're on the second run of this loop. Print hello. We print our second hello. Total is 1. 1 plus 1 is 2. Stored in there. And then we're on our third step of loop. Print hello. 2 plus 1 is 3. Store 3 in total. So we run it. I said we run it, not hit we hit F5, not 5, and we get hello, 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 3. This is what an accumulator is. It's where we basically can count up something. We can do a running sum. Okay. Any questions so far? Right? All this does is a for loop does exactly what's inside of it, as for an exact number of times. And as we see later, although this class I try not to do this too much, but as we eventually do see later, what we can throw inside a for loop is completely arbitrary. There's nothing stopping us from, of course, doing the completely horrible thing to students and doing this. Right? Which is to say, you can have for loops inside of for loops. We're not going to be using that today. We're not going to be using it the next day or the day after that. It's going to be a while before we actually have to use for loops. And Python is very good at giving you tools to avoid doing for loops inside for loops. But what this simply says is that we have a loop that's going to run 3 times, and each loop, we have a loop that's going to go 3 times. So we're going to do hello, world, world, world 3 times. Okay? And this does that because it's inside the for loop. If it wasn't inside the for loop, it would be hello, 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 world, 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 right? If it's inside the for loop, it's indented. Okay? Now, the other bit is the world is going on. So how does this actually work? Well, the way this works is that the for loop iterates over something. The grammar is actually for thing in collection. Okay? For thing in collection. And it's a bit easier to show with an example of this, of how that works. Word is equal to hello. All right. So for letter in word. Now, word is a variable I just created over here. Okay? It's hello. Letter is a variable I just put here. I can put anything I want here in this second spot. You put blank if you don't care about it. But a lot of times you do. The most common thing you'll see put in here is I for integer. But over here I like to do just simply for letter in word. I like to make the thing I'm doing make sense, because the way it works is for thing in collection, and a word is just a collection of letters. So the way we do this is print. Oh, and all this is in the lecture videos that I did in the textbook. But the reason I'm doing this here is because it's worth it to do this multiple times. Okay? So word is equal to hello. For every letter in word, print out that letter. So we had hello, so it prints out H-E-L-L-O. It goes through those each step of the way, right? Goes through of that. If I said hello world, hello class, how are you today? Question mark. If I did, you can type whatever you want there. I can make it longer. No matter what I make it, it's going to go through each letter one at a time. Well, actually, specifically, it's going to go through each character, but letters are much shorter for me to type than character and easier to spell. So I just did letter. And so for letter, so H is ELLO space WORLD period space. So it prints out every single glyph in that string, right? It goes through and does that. And that's the way the for loop works. It says, okay, I have a collection and I want to go through each thing in the collection. Okay, so what in the world is range then, right? So instead of deleting this, I will just simply comment it out and move down. Okay, what in the world is range? This is the typical way we'll see range done. For I in range and then some number. Print I. Now again, when we were doing turtles last time, we didn't care about the variable. We didn't care about this variable. We didn't care about, so we just simply put an underscore there. So we could do I in range. I like to do, in this case, num in range because it makes sense. So for each number in the range, 5. It's actually here an abbreviation for I in range 5. Well, none of those are 5, right? 0, 1, 2, 3, 4. What range does is that it prints out all the numbers from, it is the range of all numbers from 0 up to, but not including 5. Now, a lot of counting in computer science starts at 0. Why? Memory addresses is one reason. Some languages are weird and they'll start counting at 1, but those are actually the weird languages. We start counting at 0. And so for num in range 5 is shorthand for range 0 to 5, but you don't need to remember that for right now. Just know it's 5 right now, right? Just one variable right now. It says we're going to start at 0 and go up to, but not include that number that we put down. So 5, 10, 100, right? And for 100, there's 100 non-negative integers less than 100, right? 0 plus the numbers 1 through 99. That's 100 different numbers. So it prints out 100 different numbers, and by happy coincidence, that means that this loop runs 100 times. So we can just simply use the range function, where we go over a range of numbers, to loop a certain number of times. Make sense? Now, why is this useful? Because we're going to be working with in a lot of cases with series of numbers that increase over time. Just like this Leibniz formula, 1 minus a third plus a fifth minus a seventh. Okay, although that does get a bit tricky. Now, there's plenty of other things we can do with this range, okay, as I was alluding to. Right, I just mentioned that range 100 is short for range 0 to 100. Start at 0, go up to but not include 100. Let me go to 10 instead because that's a bit easier because we can actually see the entire output on the screen. Right, it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Making sense so far? Right? Start at 0, go up to, but do not include 10. If I change this to 5, it would go 0, go up, start at 0, go up to, but do not include 5. Okay? If I said 2, this would mean what? Start at 2, go up to, but not including 5. By happy coincidence, we can easily figure out how many times this is going to loop by taking this number and subtracting this number from it. 5 minus 2 is 3. It's going to loop 3 times. 10 minus 0 is 0, so I know that range 10 is going to run 10 times. It's just, so we have lots of different powers to modify this. But for the most part, we're going to just be doing this. And we can use this, and this variable exists it gets created and gets changed every time we do a loop. We can do, so let's go ahead, I'm going to modify this print statement slightly. I'm going to go maybe something like print hello period, num is now, comma, num. And that comma tells allows us to basically concatenate these things together automatically with the print statement. Hello, so in our first iteration of the loop, or perhaps our 0th iteration of the loop, num is 0. Then in the next iteration of the loop, num is 1. And then num is 2. And then hello, num is 3. So it increases throughout this. Now again, we didn't need this in the turtle one exercise on Tuesday because we didn't care about this variable. We were just telling our turtle to do something a repeated number of times. We didn't care about the number. But for this one, for this formula, we are going to care about it. Now let's go ahead and re-examine the formula. Okay? And this is one of those cases that you may feel like I am going to say, and here's the basic, and now we're just going to jump through intermediate straight to advanced. But that's only because numbers are scary sometimes. I will try to go over this. Please, if you feel stuck or not understanding, please do not hesitate to bring it up, because I guarantee you there's about 20, for about one each person, there's probably about 5 other people who are unwilling to ask the question. All right. So the Leibniz formula, it says, so today's objective is we want to try to do as much of an accurate calculation of pi as possible. And the Leibniz formula, the Leibniz-Madhava formula, says it's 1 minus a third plus a fifth minus a seventh plus a ninth, so on and so forth. That gets us close to pi over 4. So we can calculate this, multiply, get our answer, multiply it by 4, and that's going to be something that's going to look like pi. And the more we do it, the closer to pi it's going to actually be. All right? So, okay. So this requires us to kind of do a lot of steps over here, right? And let me just go ahead and just add in that last bit about accumulators. Just tie that in for a second. One common thing we do with accumulators is we do something like this. Total is equal to 0. Hello, num is now this. Print. Let's go ahead and get rid of the hello. Num is now this. Total is now total. And now what we're going to do over here is we say total is equal to total plus num. Okay? Oops. That happened because I accidentally deleted my colon. Okay? So in our first step of the loop, actually let's go ahead and break this up a bit easier so that we can see a visual break between each iteration. Num is now 0, total is now 0. So we start off from going over all the numbers up to but not including 5, starting at 0. 0 plus 0 is 0, so number is 0. Total is now 0. Num is 1. Might be easier for you to digest if I put this in between. We take 1, add it to the previous total, and total is now 1, because 1 plus 0 is 1. Then we go over to, oops, didn't print out the right thing. There we go. Then we set number equal to 2. Number is 2, 2 plus 1, which is what we had at the previous statement. Number is now 2, 2 plus 1 is 3. Next number becomes 3. Total is now 6. Why? Because we had 3, we added 3 to it, and now we have 6. 6, we had 6. Now we add, now number is 4. We add 4 to 6, we get 10. Now, if you have a particularly good memory, a ridiculously good one that happens to notice a few weird things that you probably don't notice. You'll notice we went over, I very briefly had the opportunity to mention this on Tuesday. Last week, when I was talking about handshakes. This is the triangular number series again. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. It's going to show up a lot. Okay? So doing things like this is pretty trivial. Adding 1 plus 2 plus 3 plus 4. So everybody can see that I'm just kind of adding up a series like this, right? To some arbitrary endpoint, right? That's what I did here, right? Now, there are different ways of doing this. And if we squint really hard, this isn't too different than actually what we have to do for the Leibniz series, right? Because the Leibniz series is 1 minus a third plus a fifth minus a seventh plus a ninth. I mean, all that's different is that it's got negative numbers in there and we're adding fractions. And the fractions are not going up by 1, they're going up by 2s. So we're only getting odd numbers. So if you squint really, really hard, it's not different at all, right? So we can use what we're doing here with the for loop and address those three separate things. The fact that we've got positive and negative numbers swapping. The fact that we're going up by 2s rather than 1s. Okay? And the fact that it's a fraction. And we can address all three of those in turn and solve this problem. So, I'm going to go ahead and give us a fresh slate. So, the first thing I want to do is address that going up by 2s. Okay? There's a few different ways we can do that. But I think that the best way to do that is by completing the idea of what the range function can do. So for num in range, okay, print num, right? This prints out all the numbers from 0 up to, but not including 10. If I put a 1 here, this is going to give us all the numbers from 1 up to, but not including 10, right? Start point, stop point, step. Start, stop, step. Now, the only one of those that was ever mandatory is this one, the stopping point. You can optionally give it a start point, and you can furthermore optionally give it what we call the step, which will do exactly what you're hoping it's going to do. Remember, least surprise here, which says rather than by default, we go up by 1s. Instead, we're going to go up by 2s. 1, 3, 5, 7. Makes sense so far? Right? Okay. 20. 1, 4, 7, 10, 13, 16, 19. I can guarantee you that on your first test, you will see a question that looks like this, where I give you a for loop that looks something like this. The math isn't very hard. The math will be something along about this difficulty. And I say, give me the output of this for loop. I'm warning you of this because somehow, last semester, about half the class got it wrong. It's not that hard. 1 to 20, up by 3s. Don't go over 20. Okay? And every year and I think last year's might have looked like this, something like this. 20 and 8. This for all the numbers in the range from 2 to 20 going up by 8s. Start at 2, go up 2, but don't include 20, go up by 8s. which means which starts at 2. 2 plus 8 is 10. 10 plus 18 is 20. And once we add another number, we're beyond 20, so we stop. Make sense? So there you go. That's your bonus for coming to class today or watching this video on recording, right? That will be on the test. Always is. And again, the numbers are not going to, I'm not going to do something horrible like this to you, right? This would just be mean, especially since I'm not giving you a calculator, right? That would be mean. I'm giving you a single digit for the step, right? And I'm not going to go above 20 because that would be mean, right? It's not pedagogically important. All the math on my exam will be fairly easy to do, okay? Right? Just to kind of aside. I might ask a question like this. What is the output of, here, I'll put in here. What is the output of this? Right? What's that equal to? Anyone? 0. It's a big fat 0. Because it's integer division, and any smaller number divided by a bigger number in integer division is a 0. We learned that in lab 2 when we see this. This is just a more hyperbolic version of that, shall we say, right? So if you see some weird math like that on my exam, that's a key to you that's a trick question, kind of a trick question. Is it really a trick question if I let you know the trick in advance? Maybe it's a double trick, double bluff. It's not. All right. So similarly, something like this, right? Something like this. 327,864 mod 10. In other words, this is asking what's the remainder after it's divided by 10. Yes. Anyone? 4. Right? It's the last digit. Similarly, let's just go with that. 1, 2, 3, 4, 5. Divide 10. About as easy to compute. 1, 2, 3, 4. Right? The math on the exam is might involve big numbers, but it's the kind of operations that you're going to be able to do without a calculator. I promise you that the most complicated math will probably be adding 16 plus 16 around that. And you should be able to do that in your head, and if you can't, well, there's plenty of scratch on the paper, room for scratch paper. And if you're really that scared, I will check your basic arithmetic for you, or your TA will. But anyway, going back to this. So this range has a lot of power. It has a lot of tools for giving us a range of numbers. That's why it's called range. It gives us a range of numbers. Okay? So the range we need is 1 minus a third plus a fifth minus a seventh plus a... No. When you see problems like this, when you see big problems, break it down into the smaller parts and then see if you can't make progress with each step. Let's not look at this as 1 minus a third plus a fifth. Let's look at it as 1 minus 3 plus 5 minus 7 plus 9. And even that's a bit too much. Let's just forget that and just do 1 plus 3 plus 5 plus 7 plus 9. Make sense? So we're going to just simply... So let's go ahead and say... Let's call this denom for denominator, because that's what we're calculating, the denominator, right? This is what the number that's changing is. The numerator is always the same. It's 1 over 1 minus 1 over 3 plus 1 over 5, right? The numerator is always 1, so that makes our job easy there. So the denominator is what's changing, and it's going to start at 1, and it's going to go up to whatever number we choose, up by 2's. So we print out the denominator, not the demonator, the denominator. Although the demonator sounds like something that you would use in a horror movie to kill demons. Okay. 1 plus, so 1, 3, 5, 7, 9. Great. Let's go ahead and now put that into our running sum, right? So let's go ahead and put that into a total. Let's go ahead and start storing these numbers. Now, common thing you might accidentally do is do something like this. Total is equal to denom. And we can say print, we can give print denom is denom print total is total, right? And again, the reason I'm just printing these out is so you can visually see what's going on. And by the way, your textbook has a great tool for this. Your textbook has a great tool for going for this. And it's going to do this better than I could. Okay, which is part of the reason why I love this textbook. Okay, if you go over here and you go into any code block, but I'm just going to use my scratch pad. If you go into any code block and I do this, for I in range 5, okay, and I do what I'm doing here. Total is equal to 0. Total is equal to total plus I. So here I'm just doing this running sum where I'm adding 0, then 1, then 2, then 3, then 4, right? Print total. Now, yes, you can run it in your web page, which is an amazing thing itself. Also, I always forget to do this, where I forget to put in that colon. So if you forget it, it tells you. It happens. Okay, and that's not the amazing part, although, again, I think it is pretty amazing that I can do this in my web browser. What's amazing is this other button here, the Show Encode Lens, which will take a second, and it's going to pull this up, where it will step through every single line as it executes and shows you what's in memory. Total is equal to 0 for I in range 5. Total is equal to total plus I. So it's going to so the red arrow is what's about to execute. And we hit next, it executes. 0 plus 0 is 0. Now this line executes again because we're at the top of the for loop. I is 1. Total is equal to total plus I. So you can see there on the right over here that as it goes through, it updates and it goes step by step through the entire code for you. So if you're getting lost in the code, you can use the textbook. It's a great tool, this CodeLens thing. Visualize with Python Tutor. I suppose you could go straight there for that, but it's fantastic. Okay. So now back to this. Common issue that we see here, that you often do here, is that we forget to do the total plus, right? We forget to do the actual addition. So, of course, it's not going to change. Total is equal to total plus. Okay? So 1, 3, 5, 7, 9. All right. The next step is to make this add fractions instead, right? I'm not going to worry about the negative part. I'm just going to turn this into fractions. And that actually ends up being ridiculously trivial and unsurprising once you see it. It's one of those things, it's like you can't unsee it once you see it. To make it a fraction, we just simply do 1 over the denominator. Because of course you do. That's how it works, right? That's what a denominator is, right? So, right, I can say fraction is 1 divided by the denominator. So our fraction is 1 divided by the denominator, and then the total is that. So, right, the fraction is 1 over 1. The next fraction is 1 over 3. So we get 1 plus third. The next fraction is 1 over 5. The next fraction is 1 over 7. And the next fraction is 1 over 9. So we just add these together. Make sense? 1 plus a third. Everybody see how that worked? All I did was add 1 over to change that from, and we went from adding 1. So let's go ahead and add another print statement in there. Print. Just to, again, these are not daemon. Denom is, for denominator, is, comma, denom. So the denominator, again, is 1. The fraction is 1 over 1, right? And I can actually, let's go ahead and I'll just add another comment over here to do 1 over denom to show what it is. Right? So we have right? For denominator is 3, so denominator is 1 over 1. That is 1.0, so the total is 1.0. Denominator is 3. The fraction is 1 over 3, which is 0.33. So the entire thing is, so total is 1.333. Oh, it's just simply, okay, that 333 is from it going off the end. That's all. It's from wrapping. Yeah, that's a bit too much information. Sometimes too much of a good thing, right? So, here we go. Okay? So, now, the last part is to get it to alternate, right? So we've done going up by 1, 2, 3, 4. We've gone from 1, 2, 3, 4 to doing. The first change was to make it do this 1, 3, 5, 7, right? To do that, and then the next change we did made it do was to put all those terms over 1. 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 7. Now, every so often, I'd like these to be negative numbers, right? I'd like it to be 1 minus a third plus, it should switch off, right? So what we're going to do is use, again, math as a tool. Notice that that's what I'm doing here a lot of the time with math operations, is I'm using the math as a tool to do something to numbers, as opposed to just it exists as a problem. Right? I use mod divide by 10 to get the last number of a number. I use, I use a number mod by 10 to get the last digit of a number. I use number divide 10 to chop off the last digit of a number. So here, right, I'm going to use another principle math as a tool, right? What we want to do is to change 1 to -1 and the -1 back to 1, which we can do. 1 times -1 turns, 1 times -1 turns 1 into -1. -1 times -1 turns it back into 1, right? If we keep multiplying, right? If you keep multiplying by something by -1, it's going to keep swapping, right? Right? Here, I'll put in a variable. X is equal to 5. Okay? X times -1 gives us -5. X is equal to, now I'm going to set that variable. X is equal to X times -1, right? That gives us -5 because we hadn't saved it yet. So now, if I do that again, X is equal to X times -1. X was -5. I multiplied it by -1. Those negatives cancel. It gives me 5. Right? Negative number times a negative number is a positive number. So I'm just going to use that tool. So I'm going to create one more variable over here. I'm going to go ahead and call it sign, and I'm going to set it equal to 1. Right? And what I'll do is I'm going to change this equation. Total is equal to the running total is equal to the current total we have plus this next term I'm calculating, which is the sign divided by the denominator. Now, doing this, all I've done is replace the 1 I had with another variable, right? It's not changing anything yet. But now what we can do at the end is we can say sign is equal to sign, what I currently have, times -1. So after I'm done with, and the reason I do this here is because I want to multiply it I want to change the sign for the next step of the loop, right? If I did it up here, if I did this up here, I'd be changing it before I did the calculation, which would mean that I would be, I'd be doing -1 plus a third minus a fifth, which is the opposite of what I want. Instead, I want to do this, and then I'm going to update it for the next type of loop, right? So fraction is, so now we need to change this a bit. fraction is sine divided by denominator. And so here we go. Denominator is 1. Fraction is 1 over 1. Denominator is 1. Fraction is negative 1/2. Let's go ahead and just remove or comment these out for a second so that we can just see the fractions. There we go. We've got our fractions. And now, rather than plugging it in manually, had I started typing this out at the beginning of the lecture, 1 minus a third, I might have gotten to this point. I might have gotten to this point. But I certainly wouldn't have gotten to this point, not nearly as quickly. Right? Now, one thing to note, printing operations are slow. Okay? Your computer can actually do this a lot quicker if it's not printing out every single step of the way. Right? You can stop that, by the way, just by using a key command. Control-C will actually do that, or Command-C. So here is what I mean. So it was taking so much time. Now I'm going to print out that total. And I'm just not going to print anything out now, right? Because we know it's alternating and we know it's adding. And that gives me this number, right? Remember, it took forever to print this all out. But now, we've got a small number. And it prints out this number, which should be amazing for us. But you, like me, we don't reflexively know pi over 4 over the top of our heads, right? Because remember, the entire formula calculates pi over 4, right? So what we should do here is we should need to multiply this over by 4. We need to multiply this formula by 4, right? We need to multiply this formula by 4 to get from pi over 4 to pi. And we get 3.13952965558 So not quite pi, right? It actually takes quite... So one thing I did not mention about this, this approximation takes a while to get to pi. It takes a while, right? Doing 1,000 terms only got us 3.1... It got 2 of these correct. 1, 4... Because it should be 3.14159. Although it's interesting that the 5926 is correct over here, right? It's actually quite interesting. And that's what makes this a fascinating one to me. Because once I go to 10,000, it goes 3.14, and it should be, instead of being 3.14139, it should be 3.1451592653591, right? You can actually check that on the Wikipedia page because, again, there's at a certain point to approximating pi where it just becomes a flex again, or memorizing pi becomes a flex, right? 3.141592653589793. 8, so it actually got pretty close over there, minus that digit. In fact, now if I went from going from 1,000 to 10,000 iterations, now I'm going to 100,000 iterations. It should not surprise you. Now that took 10 times as long, unsurprisingly, because I'm doing 10 times as many calculations. But for a modern computer, doing 100,000 additions isn't really anything to really scoff at. 1 million? Sure, no problem. It just kind of hung there for 1 second, though. Just like for not even a second, a smidge, right? And when I go over to 10 million, though, that's going to be 10 smidges. Right? 10 smidges worth of time. And then this would be 100 smidges worth of time, where I'm doing how many is this? 100 million. 100 million, right? So it's taking 10 times as long. So because I'm multiplying the number of calculations I'm doing by 10. Now it's certainly going to complete, but it can take a while. Would take a lot longer if I was printing everything out, too. But that is our formula. Now, a lot of the stuff you'll be doing in class with for loops in Lab 4 is going to be which is you don't have to worry about because that's what it gets introduced next week, is going to be a heck of a lot easier. Specifically, Lab 4 is double length because it's going to be both Lab 4 and 5. In fact, if you check our module page, right, if we go to canvas.temple.edu, we go to our modules. Is Duo finally going to ask me to log in? Nope. Okay, great. Okay. By the way, the image over here, if you couldn't tell, is AI generated because felt like that was a good use of AI there to generate a silly Python trying to teach coding. All right. So, anyway, if we go to modules, yeah, that was its own little adventure. If I tried to get people teaching, if I specified Python programmers learning Python, it would actually create it would alternatively create snake people as well as people dressed in hoodies of snakes. You know, it was pretty funny. It would get the coding part right. Anyway, so if we check over here, modules 4 is turtle sequences and for loops. Lab 4 and 5 does for loops. Okay, so so notice that for module 5, I don't assign anything new. I assume that this one is going to take extra length of time. Okay, but again, you're all you care about right now is Lab 3 where you're at. But I just wanted to make sure if you're like, oh God, I have to get this. This is a lot to understand. I'm going to have to get it all at once. No, this is something that we're going to be hammering for the next few weeks. Okay. Now, with regards to, but this is, again, it's pretty funny to see that is what converges to pi. And that's the technical term. We're converging to pi. There's other formulas, other approximations for pi, by the way. And they can and a lot of these iterative ones can be done. Okay, there was, let me go ahead and just, right, so, no, I want approximations of pi. Okay, so this is the Leibniz. Here we go, approximations. Okay, so, right, we have, then there was also this formula, which had this whole complicated thing of pi over 2. This calculates pi over 2, which is the Wallace formula. And we could ostensibly, if I had more time and you're not here in a math. You're not here for the math. So if you had the interest, you could do the same thing to calculate this thing. Only we'd be multiplying rather than adding, right? Because it's also a formula. 2 over 1 times 2 over 3, which is then multiplied by 4 over 3 times 4 over 5. So 1, 3, 3, 5, 5, 7, 7, 8, 2, 4, 6, 8. Right? That's our pattern. The numerators keep going up by 2s, and the denominators keep going up by a different kinds of 2. In a different stepwise thing. Other algorithm. So in 1910, Indian mathematician Ramanujan, he found this converging series. He was a brilliant mathematician, by the way, like one of the most brilliant mathematicians ever. So this particular thing, this goes to pi. So there's a lot of different things, and it's been and the reason that computer scientists care is because that's kind of a thing to throw supercomputers at universities at to kind of prove how powerful it is. A lot of these are using something called Y-Cruncher, which is, I don't know if it defines that there. Oh, yeah, with use Y-Cruncher. So the current record is the storage review team with 2.2 digits, which is the Chudnovsky algorithm, which a fast method for calculating digits of pi based on Ramanujan's pi formula, which is the one I kind of just gestured at. So it calculates this. What is k in here? K is, I assume, as k approaches infinity. So as we increase k, the closer k gets to infinity, the closer we're going to get to 1 over pi with that formula. It's a ridiculous formula to look at, and personally, it's like huge, It just kind of looks like people just threw random numbers together, but apparently this is what works. You're never really sure when random numbers throwing together is going to be useful, though. Anyway, so that is today's lecture on for loops. Now, next lecture, before I completely dismiss you, right, so Lab 3 will be over turtles. You do not have to use for loops, although it will help. On Tuesday, we are going to use for loops again for testing with random passwords. And we're going to be doing plenty of using for loops in the next couple of lectures. Okay? It's just going to be all for loops all the time for a bit. All right, take care.